Hey, welcome back. This is Daniel, and in this video we'll be discussing monads. Now, monads are a notoriously difficult topic in advanced functional programming, so the purpose of this video is to strip away all the psychobabble and just focus on the essentials. This is going to be slightly theoretical, but you will not escape coding practice, I promise you. Cool, so what's a monad? Before I talk about what a monad is, I want you to picture a list of elements. Okay, so have this in the back of your head. So monads are an abstract type. They're actually a kind of types which have some fundamental operations, like a list. So if I declare a monad of a given type parameter, the two fundamental operations of a monad are unit, also called apply in Scala, or pure in other languages, and the unit operation constructs a monad out of a value, or out of many values. The other fundamental operation is flatmap, also called bind in other languages. And flatmap transforms a monad of a certain type parameter into a monad of another type parameter. Now, given these two fundamental operations, we have a lot of monads in existence, such as list option try, which you've already seen, future you will see in the concurrency chapter, stream that you've already implemented, and a lot of collections and a lot of computational types. They're all monads. Now, besides these fundamental operations, monads need to satisfy some monad laws. There are three monad laws. One is called left identity. That is, if you build a basic monad out of an element and you flat map it with a function, it should give you the function applied to that element. And in reverse order, if you have a monad instance and you flat map it with the unit function, then it should give you the same monad instance. Now, the third monad law is a little bit more complicated, and it's called associativity. And it says that if you have a monad instance and you flat map it with two functions in sequence, then that should give you the same thing as flat mapping the monad instance with a composite function that does f flat map g for every element. All right, so because I asked you at the beginning to picture a list of elements in your head, we're going to see how these operations and how these monad laws apply for list. So let's see. First monad law, left identity. Let's see it in practice. So unit for list is just the apply method of the companion object for list. So list x flat map f, what does that give us? Well, it's f of x concatenated with nil flat map f, and nil flat map anything is just going to give us nil, so that is going to be f applied to x, which satisfies the left identity law. Next law, right identity. So if we have an already constructed list and we flat map it with unit, that is x arrow list of x, well, that's the same. Next law, right identity. So if we have an already constructed list and we flat map it with unit, that is x arrow list of x, well, that's the same list instance. Now, for the associativity law, let's break it down with an example list of three elements, and I named this ABC in yellow on the screen so that you can see it more clearly. So a list flat map f flat map g, let's break that down. So flat mapping a list of three elements applies f to each of those elements and then concatenates the results. But if we decompose that, we'll get to fa flat map g concatenated with fb flat map g concatenated with fc flat map g. But these three things are similar, so that will be the same thing as abc flat map this guy, which is the same as in long form abc flat map x arrow fx flat map g, which is the exact expression that the associativity law asks for. So all of the monad laws hold for list. Now, if the associativity explanation was too quick or you found it too complicated, feel free to pause the video and try to prove this for yourself. But the inference chain goes like I've shown you here. Let's do another example with options. Options are another monad, and we're going to prove that options satisfy the monad laws. So let's go with left identity first. Now, before I go on proving the laws, just to mention that the none case for option is very trivial because none flat map anything will just yield none, which proves the laws immediately. All right, so we'll focus on the sum case. All right, so here it goes. If we construct an option with a non-null element and flat map it with a function, then option not null will build a sum, and flat mapping that with a function will lead to f applied to that element by the sole definition of flat map on sum. If you take a look at the implementation of sum, that's exactly what flat map actually does. All right. Go on to write identity. So write identity says that if I have an already constructed option and flat map it with unit, and unit constructs an option out of an element, then I should obtain the same monad instance. So let's prove that. Our original option is sum of some kind of value, and then we're flat mapping it with some function. And by the definition of flat mapping on sum, that will apply the function on the value contained within the sum. So that will construct another option with a non-null value, which is sum with the same value, which is the original option that we started with. Now, let's look at associativity. So associativity says that if we want to compose an option by flat mapping it with two functions in sequence, that should be the same as flat mapping the same option with a composite function, which for the x element contained within, it applies f flat map g. So how does this work? So let's compute the left and the right hand side of this equality separately, and let's prove that they do the same thing. So if we construct sum with a value and then flat map it with two functions in sequence, then sum v flat map f is f applied to v by the implementation of flat map on the sum case class. All right. So we have that, and then the right hand side of the equality is sum v flat map with that composite function will apply the composite function to the value inside. So that will lead to the same result fv flat map g of the left hand side of the equality. So the associativity law also holds for option. Now, I know all these explanations might have been slightly mathematical, slightly abstract, slightly theoretical, but let's get back to our IDE and let's implement our own monads. All right, so as before, let's create a new Scala application and let's try our hand at some monads. So right click on the part2 AFP package, new Scala class, and name this monads. Make it an object and make it extend app. Okay, so let's try our hand at implementing our own monad. So let's write a simple implementation of the try monad that we often use in practice and that we discussed in the beginner's course, although we only discussed it in terms of how to use it, not in terms of how it's implemented. So let's call this little trait, instead of try, let's call this attempt of some type A. Okay. And in this trait, we'll implement the famed flat map of type B. And this takes a function from A to attempt B. And this will return an attempt B. And the unit fundamental operation, we'll implement that in the companion object for attempt. So let's create an object attempt. And let's define an apply method, which builds an attempt out of a value. And we'll use a call by name argument. Because we don't want this argument to be evaluated when we build the attempt, because the evaluation of the parameter might throw exceptions, and we want to prevent that. All right. So we're implementing our own try monad. All right. So if you remember, try is a computation which might throw exceptions, but it will not blow up in your face and will contain the exception within if it does happen. All right. So try has some case classes. It has a case class success of a type A, and this contains a value of type A, and this extends attempt A. All right. And a case class fail, or failure if you want this as a name, and this will contain the exception that could be thrown inside. So this will contain a throwable, and this extends attempt of nothing. All right, so let's make this covariant and make fail extend attempt nothing. So let's define our little flat maps inside, and the type A in the case of fail is nothing. Okay, and let's put some question marks inside so that we can implement them in turn. All right, so what did we write so far? So up to this point, we wrote the prototype of our attempt monad, in that we have the unit method, which creates a monad out of an expression which might throw an exception. That's up to the implementer to actually handle that. And then the fundamental operation called flatMap, which takes another type parameter, and a function which transforms an element of type A into another attempt of type B. All right, so this is the prototype of our attempt monad. All right, and the case classes here are just our implementation details, and they extend attempt A, and they should both validate the monad laws, but we'll prove those after we implement them. All right, so let's go ahead and just implement these. Now, the functions themselves will be quite simple. Let's start with the unit or apply method, which builds an attempt out of an expression which might throw an exception. All right, so the implementation here is just going to be try, like the proper Scala try expression, and here we'll try to build a success out of the value that we receive as a parameter. Remember, this is a call by name, so trying to build a success will evaluate the parameter A, but if the expression for the parameter A throws an exception, then we'll catch it. And if we catch any throwable, then we'll return a fail. Right? So this is the entire unit implementation for our attempt monad. Now, as for flatMap, it's also going to be fairly simple. Now, flatMap for fail is simply going to return the same failure, because failure flatMap anything will return the same failure. There's no point in applying F to anything. Right, so fail flat map anything will just return the same failure, and flat mapping with a success will attempt to apply F to our little value. So we'll say try F value, and in the case that the implementation of F here throws an exception, then we'll catch it. Throwable. And then in that case, we'll just return a fail. And that, my friends, is it. We've implemented our own little monad. Congratulations. Let's prove the monad laws, which are pretty simple, and they mimic the option proofs. First law is left identity, which basically says that unit flat map F is F applied to the value inside. In our case, attempt with a value dot flat map F is F applied to the value inside. Now, attempt X, if X throws an exception, then attempt X will just be a failure, and flat mapping that will just fail. So this doesn't really make sense. This only makes sense for the success case. All right, so success X flat map F is what? Take a look at the flat map implementation here. So it will return F of the value inside. And if F throws an exception, then that will be a fail. So this is actually proof. Right identity. An attempt flat map unit, then that should give the same attempt. Well, let's have a look. If attempt is a success, success x flat map x try or attempt x, well, that will return the function that is attempt x applied to the value x, and that is attempt x. But because x is a proper value that doesn't throw an exception, that will be success x. Right? Now, if we have a failure with whatever, then flat mapping that with anything, then that will just return the fail with the same throwable. Because flat mapping, the fail just returns the same instance by the implementation of flat map on the fail case class. So the right identity is also proven. Now the associativity is going to be interesting. So let's remember what associativity says. If we have an attempt, flat map f and then flat map g, then that should be the same as attempt dot flat map, and then for the value inside, f applied to x, then flat map g. All right, so let's prove that. For the fail case is fairly easy. So if attempt is failure with some throwable, then flat mapping in turn will just lead to the same fail, because flat mapping a failure with anything will just return the same object. But of course, fail e flat map this big thing will also return the same fail, because flat mapping a fail with anything at all will return the same instance. So fail satisfies the associativity law. Now, success is more interesting. So if I have success of some value, then flat map f flat map g, then that is either this guy. So take a look at flat map for success. It just returns f value flat map g if f of value doesn't throw, or fail with some throwable. All right. Now success with the same value flat map, and then for the x inside, f x flat map g, then that will be f applied to v flat map g if this guy doesn't throw an exception. Well, this guy doesn't throw an exception only if the f value doesn't throw an exception. So it will be fv flat map g or fail with the same throwable, because f will throw the same throwable both in this case and in the second case. So the result here is the same, fv flat map g. So the left hand side, success v flat map f flat map g, which is the left hand side of the equality, gives the same result as this guy, which is the right hand side of the equality. So congratulations, we've implemented a fully functional monad. So now you can feel free to just play around. So if I say val attempt equals attempt and then throw new runtime exception my own monad, yes. Then if I print out attempt, then I should see a fail here. All right, so the attempt monad works as expected, and it behaves as a monad, which is much more important. All right, so we have fail with the runtime exception with this message. All right, congratulations for implementing your very first monad. And here comes the exercise. I want you to implement your own monad, and in this case, I want you to implement a lazy monad. Now, in much the same way as option abstracts away a computation which might have a value or not, and attempt or try abstracts away a computation that might fail or not, lazy abstracts away a computation which will only be executed when it's needed. All right, so what I want you to do is implement unit or apply in a companion object for the lazy trait, all right, and the famed flat map, which flat maps a lazy monad with a function that transforms a value into another lazy instance. All right, so think about how you would do this. This is probably simple to implement or simple to write, but it's not simple to think about. All right, so take the time to think about how you would implement these and how to respect the monad laws. So that was the first thing. Okay, the second thing that I'm going to ask you to do is the following, and I'm going to give you some context. So monads, as you saw, are a kind of computation that have these fundamental operations like unit plus flat map. An alternative way to define a monad, and you'll probably find this in articles or in online, you'll have monads as an alternative definition as unit plus map plus flatten, which are two other fundamental operations. So I want you to think about how to transform a monad defined with unit and flat map into a monad defined with unit, map, and flatten. So basically, I want you to implement map and flatten in terms of flat map given a monad T. So if I give you a monad T with a flat map of type B, which receives a function from T to monad B. All right, so assume this returns a monad B and it's already implemented. How would you implement a map which takes a function from T to B instead of monad B? All right, and this returns a monad B. So how would you implement this, and how would you implement flatten? So flatten takes a monad which is composed, that is a monad of T. So I want you to flatten this out into a simple monad T. All right, so think about how you would implement these given a flat map that's already implemented. This is pretty theoretical, but I want you to have list in mind. All right, so how would you implement map and flatten with list if I gave you a complete and correct implementation of flat map on list? So take the time to solve this, and I'll come with solutions in the next video.